Well, welcome everyone again. So hope you had a great weekend. Don't forget that you live in Utah, so you should go outside, go skiing, stuff like that. How many people went skiing over the weekend? Really, like 3? Wow, we should work on this. Yeah, so it's a great place. We have to go, like, really use this opportunity. You're like, on a good day, you're 40 minutes away from a ski resort. On a bad day, you're 3 hours away, but that doesn't matter. Any questions about anything before we start? All good? Homework, moving slowly. So you have 2 weeks. I advise you to start early. Quiz was due yesterday, right? There will be another one later in the week. Don't forget to read the assigned reading materials. They are important as well, because they will help you to do the homeworks and to do well with quizzes as well. Okay, so today our plan is to understand how the functions are being called. It seems very naive, right? Because we all were programming stuff. We know what the functions are. Like, it seems that it's very easy, but still there's like a couple of things we need to understand. So, and those things are called calling conventions, right? And it's kind of, again, why is it important? It's important because you want to load a process in memory. Guys, we can solve it maybe later, this discussion. You want to load a process in memory, right? If you're here, let's just pay attention. If you want to discuss something, just go outside and do it there. What I was saying. Yeah, you want to load a process in memory. You kind of can have an idea that you can jump to the very first instruction of a program. The question is, what needs to be set up if this function is made? What needs to be set up for this function to execute correctly? And this will become clear from today's lecture. And then later on, like next week, we'll start on looking what is there really inside the process, right? And then we will understand how to actually create one. And then we will go and like learn how to boot into the operating system kernel and create a new process. Okay, let's take a look. So just a quick recap. Stack, right? So we looked at it last time. So stack is just a region of memory. So it's marked this green on my slide. It's pointed by the special register, ESP stack pointer register. And typically on most architectures, it grows towards the 0 address, right? So essentially, if you save something on a stack, let me just quickly erase everything. How do we do this? Only like this. Just a sec. So if you save something on a stack, it gets here, right? Instead of like being here. And then the stack pointer is moved, and the next value will be saved here, and so on, right? So we understand that, right? I mentioned that you're free to set the stack pointer. So it's actually not a privileged register. So any program, any C program, any program in any language can say, well, if I'm allowed to invoke a bit of assembly, which is true in C because you can either link against an assembly function or just use an inline assembly, you can set ESP to anything. You set it to 0, what happens? On the next, let's say, well, depends, but really, it just wraps around, right? The way it works, I think it will happily overflow instead of stack faulting, and we'll try to actually write something here if you push something. And if this region of memory is mapped, then you're okay. In a kernel, you will be fine. In a user land, like in a user process, as you say, it will be a stack fault because this region is likely unmapped. Why is that? Because we will see later that the top of the address space is a little bit special. It's dedicated for the devices. Like you write into this address of memory, and it really goes to one of the devices on the PCI bus. But really, you can do those tricks, or like if you really want to have fun with your C programs, just go for it. And I'll show an example later how you can implement cooperative multi-threading with those tricks. So essentially, kind of in one program, launch multiple threads, and they behave kind of like threads, right? So, but really, it's just started as one program and you don't have any support from the operating system for creating new threads. Okay, so stack can be anywhere, but you just have to know what you're doing, right? If I ask you a question, why do we need stack? What's the main reason? Correct. So you say for function frames. I want to hear slightly something different. So function frames, and I will explain them today, they are there for real. And you say, look, yeah, I agree with you that being able to allocate memory for local variables is also important, right? However, even more important, and I would say that this is the most critical reason why you need it, is to be able to remember how to return from a function. So every time you call a function, you save the address from which it was called. Or more specifically, you will say the next instruction after the call instruction. And then the ret assembly instruction will fetch this address from the stack and jump to it, right? And that this way you will continue from where you called the function, right? So essentially it allows us to invoke functions and procedures, right? So again, this is the example which illustrates my point. So it's the same function foo, which is implemented, let's assume here. And it can be called from two places in the program, right? So really, when you called foo from here, you want to return back here at this label A. And if you called it from here, you want to return to this label B right after this invocation, right? And so when you call foo, this address A is saved on a stack, right? And this way you can come back, right? But as you say, there are some additional things we have to remember. So again, the way it works is that when you call a function foo, this saves the address of the next instruction on the stack, right? So specifically, this address A, which is the size of this instruction or current value of the instruction pointer plus the size of this instruction, which is here, is saved on a stack, and it will be this A. So it gets saved, and then your ESP gets adjusted, so the next value will be saved here and will not be overwritten, and your instruction pointer goes to the first instruction of a function, right? When you're about to return, when you reach this ret instruction, it looks at what is there on a stack, picks it up from here, and jumps to it, right? And adjusts the stack to make sure that this, like, to deallocate the space, making sure that we can reuse the space again, right? Okay, so we got this point. Actually, somehow those slides, we have all of it already. That didn't get deleted somehow, apologize. And the second thing which you mentioned, you said, okay, we need, what is it I'm trying to show here? I wanted to essentially illustrate how it works, right? So just go step by step. So essentially, if you have a stack here, and apologize for just restart. If you have, that was supposed to be straight. If you have a stack, so you have instruction pointer pointing ESP here, and you invoke function foo, what happens is that you push this address, let's say it's A, on a stack, right? Your stack, in my examples, address 0 is here, so it grows this way. ESP gets adjusted to point to this line. So what happens now? You enter the function foo. Is that I'm trying to, this is a better example. So you say, if A is 0, you immediately return. Since A is 4, we decrement A, call foo again. Imagine this is address B. It gets pushed on a stack here, B, right? You again enter function foo. A is now 3. You again reach this line, push B again, invoke the foo recursively, A is 2, same thing, B. A is 1, same thing, B. At this point, A is 0, right? So you reach this branch, you say, well, start returning, and you essentially pick this value and you jump back to B. B says, do nothing, just return. You pick this value. Again, where are you going? You're going to B, you land on this label again. So you, again, just simply returning and so on. And at some point you reach the label A, right? And your stack pointer again points to the same allocation on the stack, right? So that just to illustrate how it works recursively, right? So it's not hard. Any questions about it, like at a high level, how it works? And now we will go into the details. Yeah.
We have a push payment.
Correct. So what you're saying is that, look, but you kind of cheated. So you said that A magically changes from 4 to 3 to 2 to 1 to 0, but where is A? So, and it didn't appear anywhere. And I will explain later today how we manage passing of arguments into the functions. So it will become clear in a second. Okay, so in order for a compiler to correctly implement everything, right? We need a set of conventions which describe how to invoke functions. So these conventions essentially will cover the following things. The main goal here is to implement those reentrant programs, meaning that you can call the functions recursively over and over and over, right? And there is a couple of questions which are not super surprising. So you say, well, how to pass arguments? Remember this, we just passed inside foo, we passed int A. And you have options here. In my example, which was just on the previous slide, A never appears on the stack, right? So it seems that I was passing it in register. That's fine. That's one way to do this, right? Another way of doing it is to pass A on a stack. So essentially push A on a stack and then read it from inside the function, right? And we will talk about how x86 does it. It does both, actually. Another question you might have is how to return the values, right? And again, you say, well, I can return values on a stack or I can return values in registers. And those conventions essentially, they vary between compilers, right? So especially back in the days, there was a variety of compilers which were competing between each other, right? The argument was that if you, for example, pass an argument in register, you save one push on a stack or one push and one pop from a stack, right? So it's a couple. Remember my Agner-Fox table. So a push on a stack, most likely it's in the first level cache, will cost you how many cycles? I think it was actually 2 or 3, 2 to 3 cycles. And similar, actually pushes, since it can be done asynchronously, you push and you don't have to wait for the value to really even reach the stack. I think it was 2, and pop might be a little longer, something like 2 to 3 cycles, because sometimes you need this value really, because if it's needed for the next instruction, there will be a stall in a pipeline waiting for this instruction to be executed, right? And those values are approximate because depending on how on your instruction stream, the compiler, the CPU can optimize and reorder instruction and execute something in between so you don't lose much space, but roughly speaking, 2 to 3 cycles, right? So that's why people were like disagreeing on that. Now, these days, roughly speaking, everything is more or less stable, and I will show you how it works. Okay, so the very first thing which those people agreed on is to maintain the stack frame, as you mentioned. So the stack frame is a specific part of the stack, which kind of belongs to the current function. So in my example here, right, a function draw square invokes the function draw line, and it passes some arguments x, y, and z into draw line, right? And so what compiler will be doing, it will create, it will follow the following convention. So it will say, okay, so I will maintain something what is called a stack frame, and I will use the frame register, this bottom pointer, which points to the frame. in this register. And essentially, when we have a function draw square, this area of the stack, which is blue here, is called the stack frame for the draw square function. And when you invoke the draw line, right? So stack again grows this way. This is the zero address in this figure. The compiler will generate a couple of things which allow you to say, look, this stack frame of the draw line will be above it, right? And again, it's a high level description here. So, but what the stack frame will contain is it will contain the local variables of the draw line. So imagine draw line declares some local variables. There will be a return address to make sure that you know how to return from draw line into this address A here, and the parameters which are passed to draw line as arguments, right? And let's just go one by one. So how it's done. So what specifically is happening is, in order to maintain the stack frame, the compiler generates two things, which are called a prologue and then an epilogue, right? So on entry to every function, it generates these two instructions. It pushes the old value of the EBP on a stack, making sure that you save the location of a previous frame and can later restore it. And then reinitializes EBP here with the current value of ESP, right? So ESP goes into the EBP, right? So the current value of the stack pointer becomes the new value of the frame, right? And then you execute the function. And when you reach the very end of the function, you say, look, I'm about to leave. So I want to restore the frame of a previous function. If everything, well, if the code is generated correctly, the old value of the EBP, which we saved here, is at the very top of the stack. And so you just simply pop it from there back into EBP, forgetting the current frame and going back to the previous frame, right? And at this point, you can return, because at the very top of the frame of the stack will be the return address, right? Agree? So it's just 4 instructions. Do you understand how it works? Any questions? Okay, so we do this. And I never explain why we need this frame. I will explain it later. So just bear with me for a second. Next question, local variables. So I kind of was saying, okay, we have those local variables, right? And again, I was asking you to trust me that I will explain what these are. And this is kind of the moment. Okay. If I ask you a question, what types of variables you know along with local variables? What else? Global. So we have local, we have global,
Dynamic.
and dynamic. And who is that person who will explain me the difference between the three?
Well, local ones fall under the scope.
Local variables live for as long as the function lives, right? So it kind of refers to the lifetime of a variable, meaning that, like, when those local variables are alive only for the duration of the function. When you exit the function, you do not have any assumptions about existence of a local variable anymore, right? What about global?
Yeah, with the lifetime, just the lifetime of the thing, that's the entire process. From the beginning to...
Right, so it's a lifetime of the entire program. And the last one, dynamic, what are those?
Yeah, just managed by the program.
So essentially managed by the program.
So like,
Yeah, dynamic or heap. So essentially you do something like new in C of some type, right? In C, you have to manage variables explicitly, and then you do, what is it in C? Free? Right? And in a managed language, which essentially says, okay, we're going to take care of your, of this new and free. There will be a garbage collector or some other trick, like in Rust, it's a type system, which will make a conclusion that it's at some point safe to do this free operation. Let me go through an example. So again, so there's 3 kinds of variables. In in our class, we kind of mainly focusing on C because that's the only thing we'll deal with. But it's not that hard to deal with another language. And if you have a class, and I can explain how it may work in some other runtime like Rust or Java or something, right? So global variables, they have in general have two flavors. One that are initialized, meaning they are non-zero, they have some value, and they will live in a specific section of a program, which is called the data section. Again, next lecture, I will explain what this is, right? So I will explain what the sections are, how the programs are linked together, and how this memory is allocated. And uninitialized, meaning that they are zeros. And there's a special section for them, which is called BSS. Do you know why we need this BSS? Why are we doing this trick? It's slightly different idea. So this is an idea for external variables, right? So, but BSS is a little simpler. So people realize if the variable is zero, you don't really have to store it on disk. Back in the days, disk space was valuable. You have a zero. Why would you store zero on disk? When you load the program in memory, the operating system will just simply allocate a page or some region of memory and put zeros there. You just have to keep the size of this BSS section. So that's the distinction. But if the variable is initialized, like if it says hello world, then you have to keep it around and then load it in memory. And that's why two different sections. Dynamic variables, as we said, new and free, they live on a heap, and local variables live on a stack. So it's a little involved, right? Because I keep throwing those ideas that there is like some data section, there is a heap, and there is a stack. So let me quickly explain. But again, I will not be super specific today, but we'll come back to it. Okay, global variables. Again, reminder, those are the variables in C and in any other language as well, but in C, the syntax looks like that, which are valid for the entire duration of a function. So you can either declare them in a global scope, meaning outside of main, right? So and it means that this hello array, which contains hello, will be valid for the duration of the entire program, lifetime of the entire program. C has additional trick. It says, okay, you can declare a global variable inside the function by using this static keyword that also says, okay, make sure that the lifetime of this is global. So if you see those, you find, right? And these are, as I said, allocated in a data section. So what does it really mean? So when the operating system creates a program, right? Imagine this is some kind of an executable file which sits on disk. Just again, bear with me for a second. When we create an address space for a program, we will create a couple of things. So this is memory. This memory, this was disk. And imagine this is 0, this is all Fs or 4 GBs, right? We'll obviously load the executable part of the program, right? Which is, we can call it a code, or sometimes it's also coded text of the program. So obviously we have to load it here, right, in memory, because the CPU will be executing it, right? So instruction pointer will be pointing here, everything like that, right? But also, as I said, there will be global variables, which will be this data section and a non-existent on disk, but existing in memory. On disk, we just have to remember the size of this section. But when we load it in memory, we say, okay, data will go here, and this guy will contain this variables like hello, which we just seen on the screen, right? And this uninitialized, sorry, like this is really, it was hello here. And those are, we don't store them on disk, but when we create a section in memory, we will just initialize it with 0, right? And at this point, the program is almost ready to run, but there will be two other things which operating system will maintain. It will say, look, I will allocate some region of memory for the stack. And remember, the stack is growing this way. So essentially, the ESP will be first pointing here and then slowly growing this way as you execute more programs. And when you return, it will be like, again, going this way just because you're deallocating space on a stack, right? And the rest of it can be maintained as a heap for allocating dynamic variables, right? So every time typically when you load a program, part of this program will contain code for implementing those memory allocation functions, something like new or malloc in C, right? So, and typically you don't implement them yourself, although sometimes you do if there is no library which can do it for you. But typically you just say malloc, but what malloc does internally, it says, okay, let's do a system call into the operating system. And remember, this is the system call which allocates memory. So who can tell me? As BRK, right, break. So, and this as break says, okay, look, I will allocate you some space here on a heap, and your current value of the process address space is this size, for example. If you need more memory, you will move this size forward, allocate even more. And out of this memory, your malloc function will essentially pick some chunks of memory to allocate smallish variables, right? That's how it kind of executes when you run a program, right? So just an overview. So what's important here that we have for today's discussion is that we have this 3 regions of memory. We have global variables, we have stack, and we have heap, right? So, okay. So just to keep going, here is example of allocating a dynamic variable in a heap. So we say something like malloc in C, please allocate me 64 bytes, and this will be a pointer, a char pointer into that memory, right? And then you can copy something like beautiful into this string and combine it with printf, which will be hello, beautiful world, right? Okay, we got it. So dynamic variables live on a heap. And finally, so I have a slide to draw you a heap, but I already did it. Finally, local variables are the variables which you can declare within a function. So without the static keyword, so just this wonderful world string. And this variable will live only for the duration of the function. And this variable will be allocated on the stack, right? So we got this idea. So why are we doing this? Why do we need these local variables? Here's an example, right, which illustrates it, right? So every time you invoke a function foo, you can say, look, inside the foo, I need these 3 local variables, A, B, and C. And obviously, every time you invoke it, you need a private instance of those variables or private instances, right? Because, for example, if you invoke the foo recursively, like in our previous example, this variable A gets updated. So essentially, it's growing. So you're passing an argument x, and A becomes x plus 1. And then you say, look, for as long as A is less than 100, invoke it again. So every time you will be invoking a function, you need an instance of this A, B, and C, right? So invoke function for once, you need them. Invoke it twice recursively, you need them, right? And as I was saying, it makes sense to allocate this variable, this space on the stack. You can play tricks in your language. So you can say, well, I have a very, very smart language. Again, just to be concrete, I think Rust does this trick. So, okay, Rust does a slightly different trick. So maybe let's skip it for now. But you can say, look, I actually can embed instead of allocating space on a stack, I can actually inject the code for a memory allocator, and which will do some malloc-like thing in the beginning of the program, allocate those variables on a heap, and maybe deallocates them here when you return, right? So what's wrong with this? Or what are the advantages or disadvantages of such approach? So essentially, instead of like allocating space on a stack or using stack for the allocation of local variables, you just go and say allocate it on a heap dynamically.
You have to make it.
You can, yeah. First of all, you need to maintain pointers, which in turn will require some space somewhere. If you're lucky, you can fit them in registers, but most likely in a general case, you are not lucky. So you will still need some space on a stack, right? And also,
It's very expensive to allocate in memory.
exactly. So every time you go to malloc, it will take you like, a very well optimized, again, if you're very careful and you care a lot about how fast you can allocate, you can probably fit it under like 50 cycles. But a more generic malloc probably takes more, like 100, 150 cycles, which means that every function invocation, which of a function which has a local variable, will need those 150 cycles on the entry and 150 cycles when you leave, 300 cycles total. So that's not ideal, right? And plus, like additional argument that you still need to maintain pointers, right? So that's why people said, okay, well, for this kind of runtime, which C is, which is the lightest possible runtime, which can advance pointers, like quickly allocate on a stack and do like that. Let's allocate them on the stack itself, right? So let's take a look at how it works. We will, every time we enter a function, we will allocate some space on the stack. If I ask you, how would you do that as a compiler designer? What would you do? Like, or not a compiler, as a language designer. You're building a runtime for C. So you need space for those variables on the stack. So what kind of code do you have to generate? What you will be pushing? Well, sorry for interrupting. Push itself advances the pointer, so you don't have to do anything, right? When you do a push, it advances. What will be your argument to push? They are not initialized here in C. C allows you to have uninitialized local variables.
Wouldn't you expect to see if you
Correct. You can have a compiler optimization which says, by the way, I'm so smart that I know that I have some number of registers and I will just assign, maybe keep this in like ECX, this one in EBX, but maybe you ran out of registers and you still need one.
So if you're on the stack, pretty much what he was saying.
No, almost. So wait, one way is to do the trick which you said, generate the 3 pushes. And you can say, wow, maybe I have to push just zeros, right? Because I don't care like what the values are. Because in my code here, there is no assignment of like 3 here. If you assign 3 to C, maybe you, instead of 0, you will put something like 3 here, or you have to, right? You had an idea. Let's imagine on 32-bit machine, int is 4. So what do? Hold on. That's why we're having this discussion. So I wanted to explain you that, yes, when you push 0, let's imagine by default you push 4 bytes. You occupied 4 bytes on the stack, right? But maybe you don't have to push 0. You had an idea.
Just subtract.
Correct. So this is what we're doing. So we're saying, okay, if we don't really care about the values of this A, B, and C, instead of like doing the 3 pushes, which again, Agnar fog, each of them, let's take 2 cycles. So it's 6 cycles total. We're so smart that we will do it in 1 cycle. And we simply just subtract 12 bytes from the stack pointer. C allows us to do that. Like if there is a bug later on because you use A and it's not initialized, C doesn't care. Like other languages do, but C doesn't, right? Okay, cool. And that's exactly what C is doing. That's the beauty of C. So essentially, I mean, beauty, which will eventually make your life very complicated. But that's exactly what you're doing. Remember, prolog, save the old frame, reinitialize the new frame. And here simply like subtract the number of bytes which you need on a stack, right? So in real life, you will see that compilers maintain something what is called stack alignment. So essentially, every time you enter a function, stack, instead of like being some random value, is aligned to, let's say, 16 bytes or 64 bytes. And so sometimes instead of saying subtract by 12, you will see some values like 16 here. That's because of the alignment, because you overallocate and align the stack. And the reason for that is that certain instructions in x86 instruction set, and specifically extended instructions which operate on vectorized registers, say that every operand has to be aligned in memory. So then, which essentially simplifies the if you align the stack, then if you have a local variable which is used in one of those instructions, it's already aligned, right? But maybe there's like a lot more details, but that's what they do. So just don't get surprised that sometimes this number is a little bigger, right? Question. Interesting. So maybe he's right. Does he have a reference? Yeah, look it up, post it in Piazza. When I was looking it up, I like GCC optimization or like manual says, okay, alignment is due to those vectorized instructions. But again, who knows? Maybe I'm wrong. Pavel is right. Okay, got it. And obviously, if we allocated something when we enter the function, we need to make sure that we deallocate the space, right? So essentially what we're doing here, and we can, like, what we can do is, since we saved the value of the ESP in the EBP here, we simply restore it from the EBP back into the ESP, right? So we don't have to do much. And then we pop the previous value of EBP into the EBP register from the stack and return, fetching the return value. So, and this is obviously very, very fast. Remember, again, Agner fog operation in the register takes one cycle, right? So that's cute. So we just simply like avoided a lot of hassle here. However, if the variable is really initialized, like if it's a equals to 3, then compilers will generate two flavors of code. So either it will be a push 3, or it will do the same trick and then simply will do a move of a 3 in one of those freshly allocated locations on the stack. Correct. And we'll get to that in a second. So just let me, like, that's a very valid point. So you say, what your classmate is asking, okay, why do we need the stack frame? And I never explained, but I already told you that I will explain a little later. So just 20 minutes away from that. Okay, cool. So we got it. Let me show you an example. So here we have a function. So with 3 local variables, right? A, B, and C. Again, we did this trick by subtracting, and that's the code which compiler with, as you say, specific optimization flags generates. So we will, maybe not today, but next time we'll like open up a compiler and see which code it actually generates. So like subtract 12 bytes. And then if you need to refer to these locations, what's convenient about it is, remember how it works. So if this was your stack, right? You push the old value of the EBP. Remember, when you call the instruction itself saved the return address on a stack, like a return of address of foo, for example, or like my function in this case. Then the next you say, well, I'll push the old EBP here on a stack, right? And then you say, I initialize ESP to be the current value, right? So ESP is pointing to here, and then you say subtract 12 from ESP. So ESP will be pointing to the value which is like 12 bytes away. So those are the locations for A, B, and C. And this is why, because I forgot to tell you that you saved ESP into EBP. So EBP actually points here, right? And if you want to refer to the first variable A on the stack, so it's simply EBP minus 4, because EBP points to the old value of the EBP. Minus 4 will give you this location. Agree with this? Similar for B, it will be EBP minus 8, because this is address 0, this is address max. So that's why the minus. And then finally, EBP minus 12 will give you this one, right? Agree? So everything, those local variables can be referred or figured out relative to EBP. So it's just a subtraction from the EBP, right? And the EBP does not change for the entire duration of the function. That's the idea of this frame. We touched it once, we sacrificed one register EBP, and now it's there, pointing to those local variables, right? like with some offset, negative offset. Okay, good. So we got how to allocate local variables. Next question. So how do we pass arguments? Again, we have options here. So you can pass them in registers or you can pass them on a stack. And actually, as I was saying, both techniques are used. So again, in this class, we are concentrating on 32-bit version of x86, right? And a specific calling convention. So I said, like, there used to be different, more exotic compilers for even 32-bit x86, which used a different calling convention. So this convention, which I'm covering in this class, has a name. And I will later point you to like a Wikipedia page, and you can go figure out all the other conventions as well, right? But good. So this convention passes all arguments on the stack and allows to return a value of 2 integers. If it's just a single integer, it just returns an EAX register, right?
Yeah.
So when you have a simple return A statement in your C program, it will be placed in EAX. And there are cases, and again, every year I keep forgetting because I almost never seen it in my life, that C allows you, like there is a case where you return something in EDX as well. And I don't remember what it is. I can come back to you and tell you.
No, sometimes you need to return 64 bits. So you can put the higher portion into EDX. So we can return a 64 bit.
All right, but what is the kind of code which you will write in C, and what kind of type you?
Long.
Long? Is that to return long?
At least the long is larger than 32 bits.
Then maybe you're right. So, but okay, let me take it offline and I will come back to you and figure it out for you. 64-bit version of x86. Just due to the fact that it doubled the number of the registers, general registers. So instead of 8, 64-bit machines have 16. They said, okay, remember, instead of pushing something on a stack and accessing it, which takes us like some number of cycles, let's say 2 to push and maybe 2 to access, they pass the first 6 arguments in registers in this order. Argument number 1 inside the register RDI. R stands for this 64-bit versions of these registers. Second argument inside RSI, third RDX, fourth RCX, and then they don't have any human readable names or like any like fancy name for those registers which are above the 8th register. So they have R8 and R9, right? And the rest, if you suddenly invoke a function which has like 10 or what is it, like first 6, 7 arguments, right? So then the 7th arguments you will have to push on the stack. And similarly, you return values inside RAX and RDX, right? So again, that's a convention. It has advantages and disadvantages. So disadvantage of this one is that you really, every time you pass an argument, you have to always push something on a stack. It takes cycles and you cannot optimize around it. So that's why x86 did this middle ground kind of convention saying, okay, if you have not so many arguments, you can use those registers, right? So which is probably faster for majority of the code we run. Okay, question.
If you use the limited number of the registers, if you do the recursion, how to recursion will actually has more and more arguments.
So great question. So imagine you, for the sake of it, on 64-bit machine, invoke something passing 1 argument, and then this one recurses passing like 9, passing 8 here, so on, right? Remember, the convention dictates that this argument should be in the RDI register, which means that this 9 has to be in the RDI register. What happens to if you want to restore this 10, what happens? What do you have to do as a compiler engineer?
The stack.
Correct. So then you have to say, look, by the way, I will have to save this RDI on a stack. Or if you do a fancy optimization pass, you may say, well, really, I don't need the stack. I will say it in some other register because maybe RSI is not used or something like that. Or maybe it's R10, right? So it depends. But in general, yes, you have to save the old value. And in a second, we will talk about yet another convention, which is which defines who has to save the registers on a function invocation boundary, because part of the registers is saved by the callee and part is saved by the caller, right? We'll get there in a second. But okay, passing arguments, as I said, 32-bit, the code which you will see in this class, 32-bit x86 code, generated on this Linux machines. The convention is called, I think, cdecal, will look like this. So if you have 3 arguments, and it's, for example, you invoke this function with values 2, 5, and 10, the compiler will generate the following code. So it will reverse the order. So it will first push the last argument on the stack, then the middle argument, and then the first argument. So the 3 will be on a stack. So specifically, the first argument, ESP, will be like this. So it will contain 2, 5, and 10, right? And then invoke the function, right? So here, what will be saved here when we invoke the function called my function? So what goes here?
Return.
Exactly. So it's return address, which is, let's say, this A. And then the function starts executing the prologue. It will save the old value of the EBP. Correct?
Yes.
And then if you need it, you will allocate space for local variables here, right? Correct? Agree with this? Again, in my example here, stack goes up, like up on a picture, down in address space. Okay, so, and this is how your stack will look like internally, right? So since we drew it, sorry, on the previous slide, so your old EBP value and the current value of EBP will be pointing exactly here, right? So in this example, stack grows this way, so this is 0. So as I was saying, third argument will be further away from your current ESP value, then 5, then 2, then return address, then your first local variable, which doesn't have a name in our example, and your like some current local variable as well, right? And you can remember I was saying that local variables, since the value of current EBP points to exactly this location, your first local variable will be EBP minus 4. The last local variable will be EBP minus 4 multiplied by the number of the local variable. Here I'm assuming that each local variable is 4 bytes, which is not always true. Obviously, you can allocate arrays, you can allocate character values, which are 1 byte, stuff like that, right? But you got the point. So, like, by virtue of fixing EBP, you can access all local variables as EBP minus something, and all arguments as EBP plus something. Since there is EBP value, old value of EBP itself, which is currently pointed by the EBP as well. EBP plus 4 is the return address. EBP plus 8 is your first argument. EBP plus 12 is your second argument. EBP plus 16 is your third argument, right? So you just go up in the address space relative to the current value of the EBP. Is that clear? Cool. So again, just to illustrate which code is generated by the compiler. So again, for this instruction, inside the function caller, the compiler, roughly speaking, generates a label caller, right? So it just keeps track of the entry point to the function. The caller itself maintains its own frame here, like old value of the EBP, initialize the new value of a stack frame by saving the current value of the ESP in the EBP here. Since it's about to invoke a callee function with 3 arguments, 1, 2, and 3, it will push them on a stack. This is the call side of the invocation, right? So it pushes 3, 2, and 1 on the stack. Then it invokes the subroutine callee, right? So just assembly instruction call callee here, and compiler will figure out like either an absolute address here, if callee is somewhere around here, or if callee is coming from another compiled module or compiled object file, then it will be a real address. So not relative, but a real one. And like, don't want to go into the details, but there's also like something what is called position independent code, and then it just generated appropriately. then when we executed the callee, right, assuming the callee returned, what we're doing here, we said, okay, we got the return value. So since we push this 3 on a stack, we have to adjust the stack back to the normal position, right? Because if you miss this, then you will never be able to return correctly, right? Because you will just return to some random value, which is occupied by one of those arguments, right? So now we say, since our goal is to compute this return value plus 5, we use the result of the subroutine, and remember that result is in the EAX register, so we just add 5 to EAX. Remember how add works in Intel assembly, so we just EAX plus 5 and save back in the EAX, losing the old value of the EAX, but in our example, it's just fine because we don't care about it. Again, restore the old call frame and return. Agree? I'll ask you one question. So where's this really return rat? So we just generated rat. So how do we return the rat? This rat variable here. Correct. So we are smart enough that we said, okay, since we're about to return rat, we'll just keep it in the EAX register. So remember, like this rat is a local variable. I was trying to say that local variables are generally allocated on the stack. In this example, which is realistic, the compiler actually says, okay, I'm so smart that I can, instead of like allocating memory on the stack, I will just reserve a register for this variable. And this register will be EAX. And that's why you don't see like reserving space, subtracting anything from the ESP here, right? It doesn't exist. And instead, the value of a rat is allocated in the register. And that's why this return simply just returns, because EAX already contains the value of this variable, right?
Why do we do plus 5 here?
It's just an example, just a goofy example to illustrate that you can do something with the return value.
Change the...
Like obviously in real code, there will be something more complicated, right? But just for...
Another one I noticed is not consistent with the previous examples that I remember in previous examples, you first push the call arguments and then EBP.
Call arguments and then EBP. No, hold on. That I wanted to emphasize that. So we're pushing the call arguments here.
Yeah.
That's the arguments for this function callee. So this 1, 2, 3, and 1, 2, 3 are pushed on the stack. Inside the callee, there will be a code which will essentially enter the callee function, callee like this, and then it will do this prolog sequence as well. And yeah, you see? Okay, I don't have an example of a no, actually I do. So this is my example for the callee function. So again, I mean, maybe it's a little inconsistent because I call here my function, but it still has the same 3 arguments, X, Y, and Z, and also has 3 local variables, A, B, and C, right? So the code which will get generated, same prolog here, reinitializing the new stack frame for this function, for my function, and then allocating space for local variables, right? And then whatever, here is the body of the function, do something, and before you return, you deallocate the space, restore the old stack frame, and return, right? And inside the function, this is how you will refer to those names. Remember the stack layout. So local variables will be EBP plus something, plus 8, plus 12, plus 16, and arguments will be EBP minus 4, EBP minus 8. As well, you can say, look, by the way, since, let's say in this example, nothing happened to the ESP actually. So ESP is not adjusted at all inside the function. So you can also refer to this as EBP minus 4 or ESP plus 8. So it will point to the same memory location, right? Okay, so we get it. So just a note here that x86 being a complex instruction set, the way they were optimizing hardware back then was that, look, since the sequence is so frequently executed, let's come up with a single hardware instruction, which will allow us to, first of all, maybe save how many bytes here. So if this is a 1 byte, This is probably 1 byte, and this is 1 byte. The whole 3 bytes we can probably encode in one leave instruction, which will save 2 bytes for the program encoding, right? And maybe we will be able to optimize in silicon. So they introduced this specific leave instruction, which does specifically this sequence of code, very specialized. If I ask you a question, what is really x86 doing today? Do they really implement leave in silicon? Like actual gates which implement the leave function? Do you guys know? Just a side note, but let's spend 2 minutes on it. No, so you get like my kids, you know, when I ask them a question about their homework assignments, they look into my eyes and they try to guess the answer. Like 7, 11, 5. Wow, it's like poker for them. So it's kind of similar. Okay, why? Why not in silicon? Who knows the answer?
Like all of the x86 instructions, since it's a CISC architecture, kind of decoded into like an internal RISC thing that the architecture actually implements.
Correct. So the irony of the x86 evolution path is that they started by building silicon for this leave instruction, so actual gates. Then it became so like, those are my gates here, whatever. It became so hard to like optimize that they said, okay, forget about it. x86 today implements a simple RISC core inside, and it has a translation engine, kind of like a JIT compiler. JIT stands for just-in-time compiler, like Java or JavaScript uses, which decodes those x86 instructions into simpler RISC instructions, keeps the cache of those instructions around of decodings and reuses them over and over and over because decoding is expensive. And then executes the simpler instruction set. So essentially, as I said, like those are probably straightforward mappings to those simple x86. They call them opcodes. No, they call them, what do they call them? Do you guys remember? Micro-ops, right? So simple micro-ops. And because those are simple instructions, micro-ops. But for leave, if they see a leave, they will internally decode it into those simple micro-ops, which will resemble something like this. Details are not very known, right? But people just, like from the public patents which Intel released, and it's kind of like, that's essentially the knowledge, right? Okay, any questions quickly about this?
How about that? We get similar enter instruction at the beginning.
They didn't have it somehow, but they had leave. Maybe they had something, and I just don't know. But leave you occasionally see, but I haven't seen it in years. But I just wanted to mention it. Okay, but now we get back to this original question. So stack frames, we spent like an hour on them, and we still maybe not convinced, as you were saying, or someone were saying, that at some optimization levels, the stack frames are actually not generated. But why do we need them to begin with? So what was the idea, and whether do we need them really at all?
No.
No. So can you tell us why?
Because as you said, we can refer to the local variable or passing arguments through the stack pointer also.
Correct. So again, I'm pretty sure that it wasn't really clear, so let me explain a little. So the stack frames are not strictly required. And so GCC compiler, for example, has this option. F stands for flag, and then the semantic name of a flag, a mid-frame pointer, which means generate code without the frame pointer. And this is the kind of the text which they have along with this flag. But don't keep the frame pointer in the register for functions that don't need one. This avoids the instructions to save, set up, and restore frame pointers, which means it saves time, right? Obviously, execution times. It also makes an extra register available in many functions. So EBP becomes your general register, which you can use for arithmetic operations and stuff like that. But it also has this statement. It also makes debugging impossible on some machines. So why is that? So it turns out that from this comment, it turns out that we need the stack frame just for debugging, it seems like. So why? Who can explain it to me?
So like say like
Correct. Correct. So let me explain what you're saying here. Let me just quickly erase everything. So, so what you're saying, imagine I assigned you a homework. It runs on bare metal, means there is no runtime, meaning that you booted it. You like it doesn't immediately explain what I'm trying to say, but there is nothing. There is no GDB, no SAC fault, nothing. But maybe you have some kind of like capability to dump the stack, right? And so if you dump the stack and you crashed, and you dump the registers, and EBP points to somewhere, you can get a lot of stuff from it, right? If the stack grows, for example, in our example, let's assume this way, right? Right above EBP, there will be a return value, right? It's just because the code we generated, right? And so we can say, wow, if we crashed inside the function foo, because we know it, we have EAP instruction pointer, which we know where we crashed. But maybe we don't know who called this function. Maybe it was called from bar, or maybe it was called from bus. And we want to know it. Like we want to reconstruct something what is called a backtrace. It's very easy here because you say, look, I will look at this return address and we'll see that it belongs maybe to bar, right? So it gives this information. Moreover, I can follow this chain of these EBP pointers, go to the next EBP pointer here, right? Right above it. So this is the EBP, like let's say -1. Right above it, there will be another return address, right? And so you can say, look, bar was called from maybe buzz. And so you can unwind this stack and say, look, this is my call chain. Eventually you get something like main function, or in case of a kernel, maybe there will be some boot function or something like that, right? But that's helpful, right? So you don't need any additional infrastructure for this unwinding. Agree with this? Do you all agree that this is a very kind of like bare bones way to implement unwind? So if I ask you a question, but can unwind be implemented without this frame pointer? So how do like mature compilers implement unwind? Do you know? Anyone? Like Rust, Java, exception handling? Right, but like what I'm asking is like a general gist of how this can be built. Correct. So, okay, what you like, good that you know. So, okay, imagine if we say, look, forget about this stack frame and this kind of human-friendly unwinding. You actually have enough information inside the compiler that compiler can say, I know the current value of ESP, and imagine there is no stack frame. So let me just erase everything here just to illustrate it. And this is how exception handling works in C and Rust and everything, right? So they don't do generate, but they can support this infrastructure without a stack frame, but they can also generate stack frame. But imagine you say, I crashed, ESP points here. The compiler just knows, it generates enough debug information, debug info, which one of the common formats for debug information is called dwarf, right? And there is another one, I forgot which one. That it says, okay, if you're in this function and your ESP is at this value, then I know that the return value will be saved here. And there is no stack frame, but you can get the return value. And again, it can do this unwind by just knowing what the program does with the stack, right? But again, it's yet another piece of infrastructure. And imagine you crashed on a bare metal, you don't have anything, you just have a stack value. For us in this class, it's easier to provide this debugging infrastructure for you, right? To make sure that if you crash inside this x86 kernel, you at least know this trick and you can unwind the stack. Actually, x86 will unwind it for you on the segfault, but if you really, there are cases where you have to extend it a little bit, right? And so that's the deal. That's how you can do it, right? A mature compiler can do it with the debug info, right? A similar debugging problem is the following. So remember, I said that when we enter the function, right, we have the following stack layout without the stack frame. ESP points to the return address. ESP plus 4 is pointing to the first argument, right? Let's imagine we just take one argument. So the current value of this location is ESP plus 4. As we move through the code, like single stepping, executing instruction by instruction, at some point we push something on a stack, and suddenly there is like yet another piece of information between the current value of the ESP, which points here, and this argument, right? So suddenly it becomes the correct address is no longer ESP plus 4, but ESP plus 8. For you as a human, it's hard to keep track of. You can, because you can like keep notes and say, well, I pushed, that's why it's ESP plus 8. But it's a little tricky. For compiler, it's not tricky. Compiler will just generate debug information for you, right? But again, for you, it's a little hard. That's why, again, by having EBP, you can, this will always be EBP, what is it, -4, something like this, right? So essentially pointing to the argument. And EBP never changes within a function. So it always stays EBP -4. You say, where is my local variable A or my argument I? You just say, okay, what's my value of EBP? You look at the stack memory and you see what was passed, right? That's your debugging routine. You can dump it as well, right? So again, compiler can do that. It's not a challenge easily, but it's hard for us. That's why we essentially, in this class, you will see code which uses the stack frame. And so, again, if you get into an argument, why do compilers skip the stack frame today, right? On x86, it was a viable argument. So it only has 8 registers, right? So not many. And you lose one of them, ESP. So only 7 are left. So essentially, you lost 14% of your register space by just reserving one register. Again, it might have a significant impact on your code, right? On maybe like even 10%. 10% slowdown is huge, right? Because why is it come? Where is it coming from? It comes from the idea that if you ran out of registers in some computation, normally you would use EBP, but now you don't have EBP, so you have to save one of the old registers on the stack, and it's plus two cycles, and maybe you have to restore plus another 2 cycles and stuff like that, right? So on x86, this argument is less pronounced because now you will be just losing 1 out of 16 registers, right? And it does have an impact. So we recently did it with my students for another project, so that's why I remember the number. So we did it for WebAssembly, right? So essentially the software fault isolation, you reserve 1 register on x86 64-bit, so pardon, on ARM, or actually on both, and you lose roughly 1% of performance, or somehow like sometimes very, like it's observable, I would say, but it's 1%. So it's not really like, I mean, if you run millions of machines and it translates into millions of dollars, maybe it matters, but normally it's so minimal that it's hard to judge, hard to like essentially argue about it. But again, what I wanted to highlight is the following. So with all my wonderful discussion about the stack frame, GCC now, the modern versions of GCC set this flag to on even at 0, meaning that unless you explicitly say, okay, do not omit stack frame, it will generate the code without the stack frame. So the code which I showed in this class requires this flag explicitly passed, right? If you don't, then it will get a functions which just do not maintain stack frame. So they bought into this argument that 1% of execution time matters. I mean, it does matter, right? So when you generate something, just don't get surprised that you don't see the stack frame, right? And the relevant section of the GCC manual is this one. So, it doesn't open. But anyway, so you can come back and look at it. So essentially, it will have all the flags and it will talk about omit stack frame pointer and what it does. So, okay, done with the stack frame. A couple of other conventions. right? I said that when we call a function, we need to make an agreement on who is responsible for saving and restoring registers, either the caller or the callee. And again, you can be flexible about it, right? And just to give you a little bit more of a context here. So the call instruction does not save any registers, right? So it just says, okay, forget about it. So we will push the return value, jump to the label, and then you start executing the callee. Callee uses the register, and who will restore it? Do you have to restore it like before exiting the function? Or maybe it's caller's responsibility to have a valid copy of this register if it needs it later, right? And so that's why the calling convention. So in this convention, which I'm describing, registers EAX, ECX, and EDX are caller saved, meaning that you invoke a function foo with a call instruction. There is no, you had some value of EAX here. You don't have any guarantees about the value of EAX after invocation of a function, right? That's logical because EAX is a register which is dedicated for returning a value, right? So naturally you will lose it. So if you need an old value of EAX, you have to push it here, do something with the new value of EAX, and maybe pop it here again, right? Or maybe save it in one of the registers which the callee has to save and restore, right? But the other two are ECX and EDX. EDX is also part of the return value. ECX is just a register to make sure that you have one. It's kind of some kind of a performance balance. So the other registers are callee saved. So if inside the function foo, you're using the, like, you're moving something into the EBX register, like moving one, for example, your responsibility is to restore the old value of EBX. So you will have to push it here and pop it before you return, right? So that's called callee saved register, the register which is saved by the callee, right? Okay, we got this one. And more or less, this is it. So, I mean, I didn't discuss the conventions about floating point register, stuff like that. They exist as well, right? So similar rules. But in general, again, there are multiple calling conventions. I describe something what is called cdecal, which is used on Unix machines these days. And if you go to this Wikipedia page, man, I hope I can go. Just wanted to show it actually. You cannot see it. How do I go back to this? Interesting. Come back here. So let me just quickly, just wanted to show you the page because it's kind of discard. Just a second. We cannot even go. But we should be able to get it. Edit assignments. Man. Here. Wiki page. Like, again, what my goal, what I'm trying to show here is that this is the convention cdecal, which I described. It will specifically talk about which registers are callee saved, which are caller saved. It will talk about floating point registers. It will provide you these examples of the code, right? And there will be different conventions, like there's a syscall convention, there's like opt-link, stuff like that. So, and for each of them, it will discuss similar issues, like similar sets. So like one of those exotic compilers, which I was mentioning, which I had when I was your age, there was Borland compiler and there was Whatcom compiler. Wow, they had different conventions, right? So slightly, you will see here that this was saying, okay, up to 4 registers are assigned to arguments in the order of EAX, EDX, stuff like that, right? On 32-bit machines. And so again, if you were opening this page, and this is a good table which like has all of these conventions, without this lecture, it's very confusing. So you don't even understand what's going on here, right? But in our case, since we kind of we talked about it. So this is cdecal in Unix, right? So you quickly can look it up. And if you forget what register does what, you quickly go to this table, just look it up later in life and be happy, like you can debug whatever you need to debug today, right? So that's what essentially the reason to show this table. And let me just finish the slide deck. So we're almost there. What I wanted to finish was just this last slide, which compares the syntax for the Intel and GNU, or alternatively called AT&T assembly syntax, right? So as I was saying multiple times, so it's very, very similar. Intel, in my opinion, is a little bit easier to read. So for example, when you copy EBX into EAX, you save EBX into AX, you write it this way. In GNU assembly, you designate registers with this additional symbol, and the order is different. So it goes this way, EBX to EAX. When you say, if I want to access 4 bytes in the memory area pointed by the EBX register and save it into the EAX, on Intel, you write it this way. On AT&T, you write it with this braces, and it goes this way, right? But I just wanted to make sure we understand it, because x86, which we use in class, will have bits of AT&T assembly, because when you, like any of the tools like compiler disassembler, like opt-dump, which we're going to use later, you can specify a flag and say, show me Intel or x86, or Intel or AT&T syntax. But when you have bits of handwritten assembly, then you make a choice. And those guys made a choice to use AT&T because it has good support for like assembly macros and stuff like that, right? So some things were easier to write. So that's why there will be bits of this syntax. Just don't get confused. Like final example, if you have something like ESI -4, this is where like AT&T really kicks in, like, and blows your mind, because who would write it this way, right? -4 brace, like, wow, really? But this is what they did, right? And so that's it. So next time we will start on linking and loading, and essentially we'll try to understand how programs are assembled together from multiple object files. What does it mean to like have a static library, dynamic library, stuff like that. Okay, thank you.
Yeah.